Alright y'all, next video starting in a new chapter, chapter 4 here. This is section 4.1, and I want to briefly talk first about the top here when it talks about what a system of linear equations is. And really, the solution to that is going to be an ordered pair. So I'm going to kind of give you some notes here. An equation is a something like y equals 3x plus 7 or 3x plus 4y equals 8. Okay, a system of equations are two or more equations. I don't know if you need to write this in your notes, but I just want to give you an example. It'd be like if I gave you 3x plus 4y equals 8 and negative 3x plus y equals 7, and being able to solve these things graphically today and as we go forward by using substitution and elimination, if you remember that. Okay, so first things first, in example 1, okay, it shows you how to determine whether it is a solution or not. It gives you the equations system, because it's more than one. It gives you the points, and it just wants you to plug x and y into x and y for this one and for that one to see if it works. And so what you'll see here, see if you can see this, is when they plug it in for the first one, right, 3 plus 1, because that's the x and y value, I get yes, and negative 6 plus 1 is negative 5, that's true, so that's a yes. You would say yes, solution. For the next one, 0, 4, they plug it into the first one, and sure enough it works, 0 plus 4 is 4. But for the second one, 0 plus 4 does not equal negative 5, and that's false. So even if one's false, if they're both false, obviously it's false. But even if one of them is false, the answer is not a solution or false. Okay? So, with that being said, I would just say not a solution. Let's look at skill practice number 1. I have it written out here. If you want to pause it maybe, try and plug in x and y into the x and y for both and see if they work. Okay? Pause it, come back, check your answers. Alright, when I plug in 6 here, I have 5 times 6 minus 2 times 3 equals 24. And I'm going to come over here and say, here I got 30 minus 6 equals 24, and that's a check. So I got a little ahead of myself there. This would be 2 times 6 plus 3. Does that equal 6? That already doesn't look very good, right? Because 2 times 6 is 12. And 12 plus 3 does not equal 6. That's a no. So this is not a solution. Okay? Or no, that's good enough for me. Okay? Probably guess that this one's probably going to work, but again, this is x and y. Plug it into the x and y. I get 5 times 4 minus 2 times negative 2. Does that equal 24? 20 minus a negative becomes plus 4. Does that equal 24? Yes. When I plug it into this one, I get 2 times 4 plus negative 2 equals 6, and 8 plus negative 2 does indeed equal 6, and so they both work, so you'd say yes or a solution. Okay, that's it. That's how you got to do it for 1 and 2. Okay, at the bottom of the next page they talk about graphing these things and showing how it works. Okay, and then they talk about how different graphs, if they cross, these are all the solutions you can possibly have. Either there's one solution, because lines will go like this, right? I'm trying to see if you can see. Will go like this, right? They're not going to come around and like reach back through here. That's not a line. That's like a parabola or a curve or something. So they'll either cross once, or they'll never cross if they're parallel, or they'll always cross infinitely many solutions if they're the same exact line. They just look different. Those are called coinciding. Okay. Now, for like example 3 says, concept connections here. If linear equations in a system represent a pair of parallel lines, how many solutions does the system have? Well, parallel lines have 0 or none, right? If a linear equation in a system represents a pair of perpendicular lines, well, perpendicular, cross at a 90-degree angle, right? We've talked about that before. Well, that only crosses once, right? One time, okay? I would, if I were you, I would probably put this box in your notes, right? With these words, intersection, one point of intersection for crossing lines are consistent and independent. If they have no solutions, they're parallel lines, they're inconsistent because there's no consistent answer, right? And they're independent of each other, okay? Now for this one, this is dependent on itself because they are the same line. It is consistent and dependent. Okay? Consistent means it has a solution, basically. Okay? It goes through here and it talks about all that stuff, but this box really is the crux of it. Okay? All right, moving on to the next page. Looking at example number 2. On example number 2, you can see it's giving you two equations. It wants you to graph them. Remember, this would start at 0 because there's no y-intercept, and have a slope of up 2, right 1. So I started at 0 and up 2, right 1, up 2, right 1. You might have to put more than a couple of points on here. I'll show you that in a few minutes. And then y equals 2, you got to remember that it's a line that goes through the y-axis. Every point on this line has a y value of 2. And where they cross is the solution. The solution is the point of intersection. Okay? Alright, so, and then they kind of went through and double checked. If I plug 1 in here, I get 2. If I plug in 2 here, I get 2. Yeah, it works. Okay? So let's go and look at a couple of examples like this, because the next one is like that as well. On number 5, again, I'm going to graph y equals negative 3x plus 0. So that starts at 0 and it goes down 1, 2, 3 and right 1. And I'm just going to go up 1, 2, 3 and left 1. And I'm going to connect my dots here. That is y equals negative 3x. X equals negative 1 goes through the x-axis where x is negative 1. And so it's a vertical line through here. Like that. And where is the solution? Well, there it is. Right there. It's kind of didn't go through my point good enough here, but you can see it. At negative 1, comma, 1, 2, 3. Right? Now let's go plug this back in and check. If I plug negative 1 in right there, negative 3 times negative 1, I get 3, which guess what? Is the y value that works. So we got it to work. Okay? Now on number 6, if you look at example 3, example 3 has, well, not a line that doesn't work out so nice. Right? It's got a line like this where I want to graph both of these lines. Well, the first line, remember how we did this, guys. When we had to move the x to the other side, we did this yesterday. And then divide everything by negative 2 to get this equation. They graphed that by plotting the 1 going up 1 over 2. And they did it a few times, and then maybe they have to go backwards. For this line, again, plus the 3x to that side, divide everything by 2 to get here. Plot the 3, go up 3 over 2. Obviously, if you do that, you just have points out here. So you have to go the opposite way to get to the point of intersection on this problem. Okay, let's kind of see what I'm talking about. Let's do number 6 here. Okay, so the first equation is y equals 2x minus 3. That one's pretty easy to graph. I start at negative 3, and I go up 2, right 1, up 2, right 1. I'm going to go down to left 1. I'm going to go up to right 1 again, and I've got this line here. Okay. Y equals 2x minus 3. Now to graph this line, okay, well, first of all, we probably got to look at this as y equals mx plus b. So let's minus 6x first. So I get, I'm going to write it up here because I'm going to run out of space here. 2y equals negative 6x plus 4. Okay. And then I've got to divide everything by 2 to get my equation, which is y equals negative 3x plus 2. So I'm going to go up to plus 2, put my y-intercept on there, and my slope is negative 3, so I'm going to go down 1, 2, 3, and right 1, and look at that. I don't even have to keep going, I'm going to do it anyway. But I see my point of intersection there. I've got my graphs. There's my point of intersection at 1, 1, or 1, excuse me, negative 1, right, because it's down. And let's go check it. This is x and y. So if I plug 1 in here, I get 2 times 1 is 2 minus 3 is negative 1. For this one, when I plug in 1 here, I get negative 3 plus 2, which indeed is negative 1. And so it works. I get to see that it works. Okay? All right. So number 7. Let's go look at example 4 here a minute. So we're going to keep doing this. But number 7 is talking about an inconsistent system, which means they're not going to cross, right? And so it's talking about parallel lines. You can see it for yourself there graphed. They're not always going to look the same, but they're going to end up being the same. And really, what makes it parallel? The same slope, right? So if you see that, you're going to see it before you even start. But let's go graph it. So like for instance, I know that this line here, see if you can see this here. Let me get up in here. Okay. That, no, you cannot see that. Let me try that again. I am going to have to zoom this out just a little bit. Hang out here. I'm 1 and 2. Alright, so this here, again, I go to plus 3 on the y-axis, and I go down 1, 2, 3, 4, and right 1. Everything is going by 2's here. I'm going to go down again, 1, 2, 3, 4, and write 1. And I can see where my line is starting. I'm going to kind of graph this in here. I might have to be more precise with my points. I'm just going to check out how does the other point graph. So this line, to solve this for y, I would minus 4x to both sides. And I get y equals negative 4x plus 8, which means my y-intercept is at 8. And I go down 1, 2, 3, 4, and write 1. Down 4, write 1. And what you'll see here is they're pretty close together here. Man, I am not drawing this accurately at all. Bear with me here. That is a terrible drawing, but you get the idea here, okay? They're parallel lines because they have the same slope, which again is going to show me that there is no solution here. And you need to write that. You need to write no solution. Just like we had to write the point here, 1, negative 1, that was our solution, and negative 1, 3, that was our solution. On this one, there is no solution, so write no solution, okay? All right, for number 8, which lends itself from example 5, as I look at example 5, again, they look really different, but when this line's pretty easy to solve. You go to 2, you go down 1 over 4, right? This line, to solve it for y, I would minus the x to that side. I would then divide everything by 4, excuse me. That's a negative 1 divided by 4 to get negative 1/4 x, plus 2, which is at 2, and then down 1, right 4. So they look different, but they are the same graph, which means they have infinitely many solutions. Okay? So how does that look on our example? Let's do the system. Let's see. Let's graph, well, this one first here. Negative 4/3 is negative 1.3, which is like right about there, okay? And then up 1/3 would be up 1 over 3, right about there, right? Down 1 over 3, right about there, and there's my line. To graph this, if I wanted to do the x and y intercepts, well, I would cover this up and I'd see x equals 4, which is awesome because that's where our point went through. And the y-intercept would be negative 4/3, which is where we went. But really, if I solve this like we're solving every other problem, and I minus x from both sides to get to here, and then divide by negative 3 into everything, these cancel. Y equals negative divided by negative is positive 1/3 x minus 4/3. And look, now we can see they are exactly the same. So again, what do I say here? Infinitely many solutions. And those of you who have had algebra might call this IMS, and that is okay with me if you say it's IMS. Okay? All right, so that's it. That's all the notes. 13 minutes, a shorter one than usual. The homework, which is on, of course, Canvas, is page 302 to 306, number 3, 6, 11 through 14. Sorry, that shouldn't be a comma. 11 through 14. 17, 28 through 29, 32, 35, 37, and 53. Okay, so it's kind of sporadic, but I try not to give you too much homework. I try to only give you homework that's really going to help you for the practice quizzes, or for the quizzes, excuse me, and for the tests. So I'm trying to make sure this stays under 14 minutes. Reminders, make sure that your reading number 2 is due on Wednesday. I sent that to you in an email doc today. Project number 1 rough draft is due on Tuesday, and the final draft is due on Thursday. Hit me up tomorrow. If you got any questions, let me know over the weekend. Have a good one. Bye.